to start the recording. Okay, there we go. Okay, so we know, based on our work in the previous section, that the natural log has some sort of inverse function, and we know its domain and range. So this notation is kind of clunky, adding the -1 every time. So instead of writing it that way, we're going to give it a new name. The inverse of the natural log is defined to be this function. So it's exp of x. Okay, and the title of the section is exponential functions. It looks like exp is short for exponential. And in fact, it really is. Exp of x is really just an exponential function. And you probably already know the base too. It's with base e. So the natural number, which is about 2.7. Okay. So how do we know that this is actually an exponential function? Well, we should really check. So does the natural logarithm undo the exponential function and vice versa? So what I should do is take the natural log of e to the x power. So that's what I mean here by this is an exponential with base e. Okay, so I've plugged it in, and if this is going to be the inverse function, then the natural log should undo the exponential, and we should get x as our answer, right? So think back to the properties of the natural logarithm, and one of the properties is that we can pull exponents to the front. So exponents inside of the natural logarithm become multiplication. This is really x times the natural log of e. But there was one caveat, one restriction on these exponents. If you think back to last time or Friday, I can't remember which day we actually talked about this, but this exponent needs to be rational. So it must be a fraction or a whole number or something. Something like that. So there's this one little bit of a problem with our exponential function. And what is the natural log of e? Can someone tell me? Does anyone know the natural log of e?
2.17? I think it's 1.
It's 1. So I don't know who was talking at first. E itself is about 2.7. But when you plug it into the natural logarithm, you get 1. And if you think back to when we were originally talking about the natural logarithm, that's actually how we defined e. So e is defined to be the number where the natural log of that number is equal to 1. Okay, so x times 1, that's obviously just equal to x. So this does work. But only as long as x is rational. because we don't actually know what irrational exponents are. If I told you to do 2 to the pi power, what would that even mean? Well, we don't really know, or at least not yet. Oops. Works as long as. Because we don't know what irrational powers mean. Okay, so in order to deal with this problem, because we don't know how to define e to the x when x is irrationals, in these cases, we have to define using the inverse function, using log inverse, which we call exp. So when x is irrational, we just say e to the x is equal to exp of x, which was log inverse. So this is actually how irrational powers of anything are defined, because, well, if you have like a whole number power like e squared, you would know to multiply e with itself. If you have like e to the 1/3 power, you would know to take the third root of e. But if you have 2 to the pi, there's no really good way to think about this using those simple ideas of multiplying and square roots and that kind of thing. We actually have to use this much more complicated idea. We actually use this inverse function to define them. And that gets us to this final part of our little definition here. For any real number x, the natural exponential function is defined to be e to the x. That's the standard notation. But remember, in order to actually tell what those irrational powers are doing, we're really looking at exp, the inverse of the natural logarithm. So exp of x. Okay, so are there any questions over this definition, or this idea? Okay, so no one is saying anything. I guess that means everyone's happy. Okay, so now let's look at an example where we have to solve an equation with an exponential function in it. So we need to get x out of the exponent. And in order to solve this, we're going to use the inverse of the exponential. So the inverse of e to the x, remind me from the last page, what should it be?
EXPX.
Well, that was the inverse of the natural logarithm. What's the inverse of e to the x? So I'm just asking you to switch around the way that we're thinking. So e to the x, we defined it to be the inverse of the natural logarithm, but the opposite also works. The inverse of e to the x is the natural logarithm. So this is the inverse of that, and that is the inverse of this. So what we have to do is take the natural logarithm of both sides of this equation. And you've probably seen this before in an algebra class or a pre-cal class, something like that. So this shouldn't be unfamiliar. So what happens over here on this side?
You
Anyone?
just end up with 3x minus 9.
Right. So since the natural log is the inverse of the exponential, this is going to undo this function and leave you with what you started with. So what you're plugging into the exponential function. So make a little note here that these cancel each other. And what you're left with is 3x minus 9. And what about the right-hand side? Is there going to be anything that we can do to simplify the natural log of 27? Maybe using the idea of exponents?
37 is 3 cubed.
Right. 27 is actually 3 cubed, so it's going to help us in a few minutes to rewrite it that way. Okay. Because, well, we can pull this exponent to the front here. So let's see. Let's go ahead and do that on our next step. Try not to combine too many things at once. So this is really 3 times the natural log of 3. And we're solving for x, so that means we're going to want to move this 9 to the right side. So what is x equal to? What's the final answer? Right, divide everything by 3. And what's left over? Well, that 3 cancels. So you have a natural log of 3. Divide your 9 by 3 to get 3. Okay, any questions over that process? Okay, so since there aren't any questions, we'll move on from this algebra kind of problem, so solving equations, to a calculus problem. So what is the derivative of e to the x power? And what we're going to have to do in order to find e to the x is think back to section 7.1, where we were finding derivatives of inverse functions, and find the derivative that way. So I'm going to start from scratch. We're not just going to plug it into the theorem. So the basic idea, if you remember, is that the natural log is the inverse of e to the x. So when we write this, they cancel each other and you're left with x. But now we're actually able to take the derivative of both sides of this equation, and that is going to be what lets us find the derivative of e to the x. Derivative of x, of course. So on the left side, we're going to have to use the chain rule. What's the derivative of the natural logarithm? Can someone remind me? What's the derivative of the natural log of x?
1 over x.
1 over x. Good. So the natural log is the outer function here. So we need this derivative, the 1 over x, but we're going to have the function e to the x plugged in. So it's actually going to be 1 over e to the x for the outer derivative. And then we need the inner derivative still, but we don't quite yet know what it's going to be. So I'm going to leave it as just the derivative of e to the x. So maybe labeling 1 over e to the x is the outer derivative, and this part, the derivative of e to the x, is the unknown inner derivative. Okay. The right side is much easier. What's the derivative of x?
1.
1. Good. So now that all that's left is to solve for the unknown inner derivative, and to do that, we'll multiply through on both sides by e to the x to cancel off this fraction. So the unknown derivative is equal to 1 times e to the x, or just e to the x. Excuse me. Okay, so here's our derivative rule. Does anyone notice something kind of unique about this derivative?
its derivative is equal to itself?
Exactly. So the exponential function e to the x is actually the unique function. It's the only function that has itself as its own derivative. So it's very important, or special at least.
Would that be true if you like for the second derivative?
Right. So if you just keep on taking its derivative, um, the second derivative would be the derivative of e to the x again. So you would just keep on getting e to the x. So no matter how many times you take the derivative of this function, you're just going to get the same thing back. Okay, and since we know the derivative, we can also add the integral rule because it's just the opposite. If I take the integral of e to the x, then we reverse the derivative. So if I start here and we end up there, except with integrals, I have to have my plus c plus a constant. Okay, so any questions about the derivative? Let's see, so now might be a good time to look at a graph. Give me a second to pull up a Okay, so what we're looking at now is, well, you can see the website here. It's desmos.com. It's a free online graphing calculator. It can do pretty much everything that a like a TI-84 can do, and maybe do it a little bit better since it's well, it's not a clunky old calculator. So I can graph y equals e to the x. And here's the classic exponential function. So we can see how steep it gets. And this is the reason why the word exponential in English is used the way it is. Because if something grows exponentially, it gets really big, really fast. So you can see how steep this curve is. Almost looks like a right angle when you zoom out. Okay, but let's go back in a little bit to where we were. And we know that this is the inverse of the natural logarithm. So let me graph them together. And one thing that we learned about inverse functions is that they're symmetrical over the line y equals x. So this line that I graphed in green, if we mirror these two functions across the line, you can see the symmetry. So the blue is the natural logarithm, and the red is the exponential. Okay, any questions before we do some more examples? So let's take these two new rules, the derivative and the integral rules for the exponential function, and just do a bunch of examples to get some practice. The first one, I want to take the derivative of 3 times e to the 3x power. So I actually have a function plugged into my exponential here. So 3x is plugged into e to the x. Okay, so let's just work through all of the details. The constant 3, since it's just being multiplied by my function, can be moved to the front of the derivative. Let's go ahead and do that. Next, we're going to need the chain rule. Because I have one function plugged into another function. We have them composed together. So the outer function is the exponential. 3x is plugged into the exponent. What's the derivative of the exponential? What's the outer derivative? It's just that, right? So when we take the derivative of the outer function, nothing happens, because we get e to the x again, and we leave the inner function plugged in. And then we need to multiply by the inner derivative. We'll try not to do too many steps at once. So here's the outer derivative, here's the inner, and then the inner derivative of 3x is just 3, of course. Let's work this way. So 3 we get from here, we have another 3 in front already. That means overall we're going to get a 9 e to the 3x. So a takeaway from this kind of example, if you have an exponential function where you're just multiplying x times a number, when you take the derivative, all that happens is you multiply by this constant. So if you take the derivative of this guy, you just multiply by 3 to get 9 e to the 3x. Okay, any questions over that first example? Okay, so let's move on and find out what happens when we plug something a little bit more complicated into the exponential. 3x is simple. Cosine is more complicated, but this is still a chain rule problem because cosine of x is plugged into e to the x. So the process is still the same. It's going to be a chain rule problem. The outer derivative doesn't do anything. The derivative of e is e to the x is e to the x. And we leave the same function plugged inside. And then we need the inner derivative of cosine. What's the derivative of cosine?
Negative sign.
Negative sign, good. So we have e to the cosine x times negative sine x. We probably want to write this in a nicer way. If you see this written out, it'll probably look like this. So the negative sign would be in the front before the exponential. Okay, any questions over that second example? Okay, so we've done a couple derivatives. Now let's try a couple integrals. I guess to get you started on these kinds of integrals with exponentials, I'll have to give you a little bit of help. When you have something in the exponent of e, let's see, I got a warning that my connection was unstable. Can you guys hear me?
Yeah, I can hear you. You're breaking up a little bit, but I can hear you.
Okay. I guess hopefully the recording that I post later won't have any of the problems, since it's just being recorded on my computer. So when we have something plugged into the exponent of our exponential, we're going to have to do some sort of u substitution. And for this particular one, we're just going to use the exponent. And this is the general, I guess the general rule when you're integrating exponential functions. You need to do a u substitution, and your u substitution is probably just going to be what's in the exponent. So 2 times x. And then du, the derivative of 2x is 2, and then we get a dx. So in order to handle this, the way that I like to do it is divide through by 2 on both sides. So we actually get 1/2 du is equal to dx. Because we don't have a 2 in the original problem. Well, it's in the exponent, but we don't have a 2 being multiplied anywhere. Okay, so we get a e to the u, and then dx becomes 1/2 du. And then we should also handle the limits of integration, the 0 and the log 3. The other way is to, at the end, substitute back in 2x, but that's not what I'm going to do. So I'm going to plug in 0 into here. So 2 times 0 is 0. And then 2 times log 3. But instead of writing it this way, 2 times log 3, I'm going to pull the 2 inside of the natural log and put it in the exponent. So this is really the natural log of 3 squared. Let's clean it up a little bit. Pull your 1/2 to the front. 3 squared is 9. And then e to the u du is left over. So since this is just e to the u du inside of the integral, we can use our basic rule for integrating e to the x, right? We just get e to the x again, or e to the u, depending on the name of our variable. And then we just have to plug in our limits of integration and find the difference. And this last step is the reason why I changed this around to a log 9, as you'll see in just a second, because when I plug in log 9 into the exponent of e, the e and the natural logarithm will cancel each other and just leave the 9 by itself. And if I had left 2 log 3 here, that cancellation wouldn't work, or it wouldn't be quite as nice. Okay, so what's left? We still have the half in the front. The e and the natural logarithm cancel each other. We're just left with 9. E to the 0 power. Anyone know what that is?
1.
It's 1. Good. Right, any number to the 0 power, well, any number except 0 to the 0 power is 1. So what we're left with here is 1/2 times 8. So that's 4. Any questions? Okay, so we have just enough time for the last example, the second harder looking integral, but actually it's not any harder as long as we do the correct u substitution. I think the weather must be affecting the internet connection. But what I was saying is, as long as we do the correct u substitution, this is actually not any harder than this easier looking integral. We just have to pick the exponent tan x, tangent of x, as our u. And then the derivative of tangent is secant squared. So du is secant squared of x dx. So the secant squared that looked like it was probably going to give us trouble actually ends up helping. It just gets collected into du. And all that's left is this. E to the u du. And now we use our rule for integrating. E to the u, its antiderivative is just itself, e to the u. But since this is an indefinite integral, I have to have an extra constant added on, just in case. And then to finish off, we'll substitute back in tangent x. Okay, and we finished right on time today. Are there any questions? Okay, so since there aren't any questions, we'll just continue this section tomorrow morning.